Hey, I'm Ryan. When you set up a vector search collection, you'll need to choose a distance metric, with cosine, dot product, and Euclidean distance being the three standard options. Many vector databases default to cosine, and for text-based use cases, that's usually the right call. But if you're building with vector search, you should understand why cosine is the default, why each of the three metrics exist, and what they're designed for. And that's what we'll be covering in this video, along with sample code and live demos so you can see each distance metric in action. And if you're just learning about vector search, you'll want to check out our What is a Vector Database video and the other episodes earlier in this series to quickly get you across the basics. But before we dive in, there's some essential terminology worth knowing first. The key terms are embeddings, magnitude, normalization, and the distance metrics themselves. First, an embedding is a vector produced by an embedding model, which is a model trained to convert input data, such as text, images, or audio, into lists of numbers, where similar embeddings are placed closer together in vector space. Next is magnitude, which is simply the length of the vector. Then normalization, the process of scaling a vector's values so its magnitude is equal to 1. This is used when you don't want magnitude affecting the similarity score. And finally, here's a quick overview of the three most common distance metrics. Cosine measures the directional alignment of two vectors, discarding their magnitude. Dot product also measures the directional alignment of two vectors, but with magnitude boosting similarity. And Euclidean distance measures the straight line distance between two vectors. Each distance metric suits a different kind of data and use case. So let's dive in, starting with cosine similarity. A cosine similarity score is the cosine of the angle between two vectors. A cosine of 0, which is when two vectors are perfectly aligned, is 1. So the smaller the angle, the higher the score. Cosine is the right choice for most vector search use cases, as embedding models encode meaning in the direction of a vector, but not its size. This means magnitude is just noise, so cosine factors it out. Now, needing to discard the magnitude value for each cosine calculation is a bit wasteful though, so most vector databases take a shortcut. They normalize vectors at ingestion and query time, allowing the faster dot product equation to be used instead. So in other words, when you're selecting cosine as the distance metric, it's probably dot product under the hood. For the cosine demo, I've used the Quora duplicate questions dataset from Hugging Face. So given a question, it's going to return the 5 most similar questions. Taking a look at the code, we're using Python with Facebook's AI similarity search library with a flat IP index. Flat means we're comparing every vector, and IP stands for inner product, which is the same as dot product. Now, in case you're wondering, why is there no cosine index to choose from? Well, this is a lower level library, and because of normalization, well, we don't need cosine. So running the script with the question, how can I learn Python programming quickly? We get 5 similar questions with the cosine or similarity scores. For most embedding models and text-based search, directional alignment is all that matters. So cosine is going to be your choice most of the time. Now let's learn about dot product. Dot product is useful when similarity should reflect both directional alignment and magnitude. A good example is recommendation systems, where magnitude can represent the strength of a user's preference or rating signal. To see the difference, let's say we're comparing embeddings for sci-fi with Star Trek and Star Wars. And I've hard-coded the values here for illustrative purposes. Cosine similarity gives both comparisons the same score, because Star Trek and Star Wars point in the same direction. Cosine only cares about the angle, so their larger or smaller magnitude is normalized away. But when dot product is used as the distance metric, the magnitude is factored in, so sci-fi and Star Trek equals 14, while sci-fi and Star Wars now equals 28. Same directional alignment, but very different scores. That's what you want when magnitude carries meaning. To see dot product in action, I've built a simple movie recommendation system using the Movie Lens dataset, feeding 100,000 reviews into a local model to produce embeddings for both users and movies. Search works by computing dot product scores for a given user embedding against all movie embeddings, then returning the top 5 highest scoring movies they haven't seen yet. Running the script for user 22, we first see their top 5 rated movies from the dataset to give us a sense of their taste. It then outputs the top 5 recommendations. Now, user 22 loves a bit of action and sci-fi, so those recommendations seem right. Switching to user 707, they seem to enjoy a good drama, so their suggestions line up as well. When magnitude carries semantic value as a strength signal, dot product is the right choice. Now let's move on to Euclidean distance. Euclidean distance, sometimes referred to as L2, scores similarity on the distance between two vectors. The smaller the distance, the higher the score. It's the right choice when vector values are actual measurements, such as sensor readings or physical coordinates. For the L2 demo, we're using the SIFT 1 million dataset, which contains 1 million vectors designed for image matching and object recognition. Each vector describes visual features of a small image patch, and you can see them rendered as colored grids in the demo. Brighter cells correspond to larger descriptor values, and because L2 distance compares those values directly, two patches will only be close together when the values in corresponding positions are similar. To perform a search, we just select one descriptor from the query set and compare it against the dataset to find the closest matches. You'll notice the closest results have a similar pattern of brightness changes, so their L2 distance is lower and the score is higher. Euclidean distance is most useful when the exact values in a vector carry meaning, since the distance between the two vectors is determined by how much those values differ in each dimension. Well, now you've got a solid understanding of how cosine, dot product, and Euclidean distance metrics work and the data types and use cases they're best suited for. If you want to go deeper or share what you're building, join the Actian community on Discord, and you can find the link in the description. Thanks for watching.